Welcome everyone to finishing chapter 18. I know it's going to be weird to not actually be able to ask questions in person, but I hope you take advantage of the time that we're actually on Zoom, whether it be the end of a lab period or during office hours, to ask as many questions as you can. I'll also keep our Zoom meetings open when that's applicable for you guys to actually talk with each other and figure out what you're missing. And then when I can, in the scenarios, I'll pop in as much as possible. So our goal today is starting to solve these problems involving weak acids and bases. Because weak acids and bases only partially ionize, remember, there is a different process for solving weak acid problems and weak base problems, such as a question that could be asking for pH. So if I ask for the pH of a solution that contains a weak acid, I can't just use this equation, pH is equal to negative log of hydronium concentration, and just pop in the concentration of the weak acid. It doesn't work that way. So we're going to have to use a different method to do so. There are two major types of equilibrium problems involving weak acids and weak bases. The first one is when you're given equilibrium concentrations for the weak acid and weak base dissociation reaction, and you're asked to find the Ka or the Kb. A second major one is given Ka or Kb, and you're tasked with finding equilibrium concentrations of the dissociation reaction. So let's look at an example problem. Example question 1. The pH of a 0.12 molar phenylacetic acid solution is 2.62. Find the Ka of phenylacetic acid. So let's increase our view on this and start filling in what's given to us. Okay, I think it's really helpful in these problems to have your previous notes in front of you so you can look through all of the different equations that we discussed at the beginning of chapter 18, so you know which ones to utilize for each problem. So what information is given to us? The first piece of information is that we have a pH, we're looking for the pH, no, we're given the pH is 2.62, and it's for a 0.12 molar phenylacetic acid solution, and what we're finding is the Ka. Okay, so that's what we don't know. All right, so I'm going to write down just underneath the problem what the pH is. So pH is equal to 2.62, and then I'm going to write down the molarity of, this is going to be, we're going to call it H-phen. Okay, the H just means that we're looking at an acid, and phen stands for phenylacetic acid. This isn't proper or correct chemical notation. It's just an abbreviation to help us with the problem, since we actually don't know the chemical formula offhand of phenylacetic acid. The molarity that's given to us is 0.12. And then it gives us an ice table. Okay, ice tables aren't always going to be given to you, but they are generally going to be utilized for these problems, so you'll be really familiar with making them. So what I would suggest in the next step, even if you don't know what to do with any of these numbers, you want to set up the dissociation reaction. So anytime you're just looking at a solution, notice phenylacetic acid solution, that just means that it's in water. The acid is in water. Anytime that we're looking at the activity or reaction of an acid and water, it's called a dissociation reaction, and that's the same for a base. So let's go ahead and write that reaction up above the ice table. Okay, so at the very top of the ice table, all that's really represented is the components of the reaction that I'm going to fill into the ice table. So what I want to draw your attention to now is what's underneath the ice table. So how did we get these three little species on top of the ice table? Well, that's because the acid, phenylacetic acid, reacted with water. It donated a proton to water. Water became H3O+, and then phenylacetic acid became phenylacetate, which is has a negative charge because it donated a proton. and the proton or the acidic hydrogen is positively charged. Okay, so because water isn't included in the Ka or in the ice table, that's why you don't see it at the top of the ice table. Alrighty. Okay, so when I'm actually filling in the ice table, I need a couple things. So the first thing is that I need the initial concentrations for each of these. And what you are filling into these boxes is the concentrations before the dissociation occurs. So that's before the acid actually reacts with water. So initial just means before reaction. And like normal, I'm going to put a little M up top here to indicate or signify that I am inputting molar concentration values into each one of these boxes. Okay, so the 0.12 molar that's given to us in the problem, that is the initial molar concentration for phenylacetic acid. So before any dissociation occurs, I have 0.12 moles per liter of phenylacetic acid, and before that substance reacts with water, I have 0 for both of my products. Looking to C is change. I know that, let me just draw a little line so that we can have a barrier between the two. The left of the line, so over on this side, is all reactants, and over here is all products. So notice I don't have any products, and I have some reactants. So that means that I can only have less reactants after the change occurs, and I can only have more products after the change occurs. I can't have less than 0, so the reactants had to turn into products. Okay, so there's an X right here, minus X, and then that means plus X and plus X for my 2 products. All right, so that makes the equilibrium easy. It's just my initial plus my change. In this case, it's minus X. And for the last 2 products is plus X. I'm going to highlight that because remember, what we're looking for in pretty much all of these problems are equilibrium values. So those are what really matter. All right, so I have equilibrium values, and then notice I'm given Ka. So I'm given at least an indication that I should write the Ka expression. Remember that the Ka expression is products over reactants, so let's go ahead and write that. So my 2 products are on the left or right-hand side of the green line. That is hydronium, and that is this phen minus, which is phenylacetate, divided by H-phen. Okay, that's my phenylacetic acid. It's just an abbreviation. Okay, so what I have so far for Ka are the equilibrium concentrations for everything in the Ka expression. So let me just go ahead and plug those in. So Ka is equal to X times X divided by 0.12 minus X. Remember, all of the concentrations are at equilibrium, so that's why I'm taking 0.12 minus X and these 2 X values to plug it into the Ka expression. All right, the objective of the entire experiment is to solve for Ka, right? That's what I'm looking for. So I have this expression, but I don't have a number yet because I have X's as placeholders for everything in the Ka expression. So that means my next goal is to solve for X. What is X? Well, looking back, let's see what other information I was given. I was given the initial molar concentration. Okay, I used that already. I don't need that again, so I'm going to cross that out. But look, I'm given the pH. So let's write down a couple of formulas that give us pH or that pH is used in. You can get this by looking on the beginning, first part of the chapter 18 notes, even a couple pages before this shows you what pH is equal to. So remember, pH is equal to the negative log of hydronium And 10 to the negative pH is equal to hydronium concentration. Okay, those are two of the main ones. You also have pH plus POH is equal to 14. There's several, but these are the main two formulas that you either use pH or pH is given when inputting a different value. All right, so I want to draw your attention to this one right here. So notice this one is telling me that if I take the pH given right here, and if I plug it in here to this expression, I will then get hydronium concentration. Now, why do I care about that? Why is that important? Let's look back again at the E of our ice table and look over at what the hydronium concentration is at equilibrium. Hydronium concentration is equal to X. So really I can kind of extend this to say if I take the pH, the negative of the pH as the exponent to base 10, that will give me hydronium concentration, which will also give me X. So let's go ahead and do that. All right, let's draw a little line right here. So if I take 10 to the negative 2.62, put that in your calculator, what I get is 2.3, just 2 sig figs, right? Because the pH, let's get this, the pH right here, only the digits after the decimal, remember? P after the decimal. If you have any P value, the only digits that are significant are those that come after the decimal place. So 2.399 times 10 to the, I get negative 3. And that is molar concentration. That is equal to your X. So let's go ahead and plug that in for X in the Ka expression. So Ka is equal to 2.399 times 10 to the negative 3 molar squared all over 0.12 minus X, which is 2.399 times 10 to the negative 3. All right, I'm going to plug that in. Okay, my final answer is 4.9 times 10 to the negative 5 for Ka, and I think that's just 2 sig figs. 2 sig figs. So take a second to double check that, pause the video if you need, and then we'll go on to our next question on the next page. All right, so example question 2 is very similar to the last question, except phrased a different way. You will still use the same basic tools to complete the problem. So question 2 states, what are the hydronium ion concentrations and the pH of 0.10 molar propionic acid? And it really should just say, what are the hydronium ion concentration? Okay, there's only one hydronium concentration. Either way, let's take a look at what we have available to us. All right, so the Ka of the acid is given. That is 1.3 times 10 to the negative 5. So I'm going to highlight that. And then we also have a pH, no, not the pH, we have the molar concentration. All right, let's do the same thing we did in the previous problem. The first thing that we did, I think, if I can recall correctly, is we wrote down that we have propionic acid and the molar concentration is 0.10. And in this case, we're given the Ka. So the Ka is equal to 1.3 times 10 to the negative 5. Then above the ice table, I write all the components of the dissociation reaction. Remember, if you're only given a solution of a weak acid or weak base, the reaction is just the reaction of the acid or base with water. In this case, we just have an acid. So propionic acid is going to go here. It reacts with water always to form hydronium ion, and then the counter anion or the conjugate base, which is Pr minus. Now again, this is just abbreviation. This isn't correct chemical formula. And let's set up the Ka expression at the bottom. So that's Pr minus times H3O plus over HPr. Great. Okay, so let's start filling in our ice table. Let's get crazy with some colors. All right, propionic acid given a 0.10, so 0.10. Hydronium is 0 and propionate is 0 because remember, at the beginning, before a reaction occurs, there are no products. For the change, that makes the change for propionic acid minus X. And then it makes the change for both of the products plus X. Then in E, I have 0.10 minus X. And for E of hydronium propionate, it is X. All right, so let's go ahead and highlight the numbers or symbols we need. Those are all in row E. And let's plug them into the Ka expression. So that gives us x squared, right? 2x is at the top, divided by 0.10 minus x. All right, notice that the Ka is given to us. Ka is equal to 1.3 times 10 to the negative 5. So at this point, it's really helpful to ask, okay, what are we actually looking for in this problem? This problem is asking us for hydronium concentrations. Okay, so that's one thing, H3O plus. It's also asking us for pH. pH is equal to what? Maybe I don't even need this little question mark there. All right, so what in the problem would actually give us these two numbers? Let's go back to our ice table. It's always helpful to do that. Look at where hydronium is. This is what we want to solve for, and notice at equilibrium it's X. So that's telling us again, we need to solve for X. Okay, we have to solve for what X is equal to. Then after that, if you remember your pH equations, remember pH is equal to the negative log of hydronium. So if I solve for X, that's the answer for hydronium concentration. And then I can also take that and plug it into my pH equation to solve for pH. So there's some cross multiplying that I need to do. I need to solve using the quadratic formula potentially. So let's go ahead and do that just below. Okay, so if I cross multiply this over, I'm going to cross multiply this over here. I will have 1.3 times 10 to the negative 5 times 0.10 minus x equals x squared. I'm going to distribute these inside. So that is equal to 1.3 times 10 to the negative 6 minus 1.3 times 10 to the negative 5 x, is equal to x squared. Now I want to get everything over to the same side, so I can set the other side equal to 0. So I'm going to have x squared plus 1.3 times 10 to the negative 5x minus 1.3 times 10 to the negative 6. So that is equal to 0. All right, that's not my final answer. I'm just highlighting it. At this point, it's really helpful if you can go back and make sure that you've distributed everything correctly, because if you do the quadratic and then you end up with some weird number and it's not right and you have to go back and correct anyway, there are a lot more steps to correct for if you continue to go on a wrong path right now. So let's go back and double check. So I've cross multiplied this over to the right hand side, so I should have 0.10 minus x, which I do, times 1.3 times 10 to the negative 5. If I distribute this into 0.1, that should give me 1.3 times 10 to the negative 6. And distributing this over should give me 1.3 times 10 to the negative 5x. There's the negative, great. And then x squared's on the right. I'm going to add this expression over, so I get plus 1.3 times 10 to the negative 5x, and I'm going to subtract this over for 1.3 minus 1.3 times 10 to the negative 6 equal to 0. So at this point, I'm going to use the quadratic formula. Some of you have voiced that you are not comfortable right now using the quadratic formula, and so that's why I wanted to use the time to do that. For those of you who would rather use your graphing calculator, you can go ahead and graph that now and then solve for your x-intercept. It's going to be the positive value that you're going to use. But I'm going to go ahead and go the quadratic route. I'm going to clear some space off for me here. Maybe you want to use a scratch piece of paper so you have more space available to you, and let's solve for x values. All right, so let's first set up what the quadratic formula is. We know that to be negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, I'm going to highlight, this is my a, this is my b, and last one, this is my c. Missed an A, there we go. All right, let's plug our numbers in. So negative b would be negative 1.3 times 10 to the negative 5 plus or minus the square root of 1.3 times 10 to the negative 5 squared minus 4 times 1 times negative 1.3 times 10 to the negative 6 all over 2 times 1. So what I would suggest doing is evaluating this expression first, and then evaluating this expression, and then subtracting them from each other. So let's take b squared. (1.3) times 10 to the negative 5 squared. This gives me 1.69 times 10 to the negative 10. All right, and then 4ac, let's do that. 4 times, let's do negative 4. Negative 4 times negative 1.3 times 10 to the negative 6. All right, this right here gives me 5.2 times 10, do positive, 5.2 times 10 to the negative 1, 2, 3, 4, 5, 6. Great. Okay, so let's plug that back in. We have negative 1.3 times 10 to the negative 5 plus or minus the square root of 1.69 times 10 to the negative 10 plus, okay, it becomes a plus because I had the two negatives, 5.2 times 10 to the negative 6 all over 2. So I'm going to evaluate this right here. I'm going to add these together. Plus 1.69 times 10 to the negative 10. All right, so here I get negative 1.3 times 10 to the negative 5 plus or minus the square root of, and this number is 5.2 times 10 to the negative 6 all over 2, and that's equal to our x values. All right, let's evaluate that. Take the square root of the 5.2 times 10 to the negative 6. Square root. So that gives me negative 1.3 times 10 to the negative 5 plus 2.28 times 10 to the, let's move this out of the way. Oops. It's a little too big. Move that little 2 out of the way. 10 to the negative 3 all over 2. And then we also have negative 1.3 times 10 to the negative 5 minus 2.28 times 10 to the negative 3, squeeze that in there, all over 2. Those are both equal to x. So let's evaluate that and see what we get. All right, so notice even before you put this in your calculator though, this is going to be a negative value, so it's not going to work. Right, a negative minus another value is going to give you a negative, so let's just go ahead and get rid of that. We know that we can't have a negative x value because x corresponds with concentration. So let's go ahead and erase that. All right, so we have this, and this is equal to 1.1335 2 sig figs times 10 to the negative 3, which is equal to hydronium concentration. All right, double check that, and then our last step will be plugging that into the pH equation to calculate pH. All right, pH is equal to negative log of our x value, which is hydronium concentration. So that tells me that my pH is 2 point, how many sig figs? 2 sig figs. So 2.95. My final answer. Yes, this is how long these problems take. This is not an exception to the rule, except that I will show you again how to make an assumption that will make the problem a lot quicker, but there's additional components to each exception. So keep that in mind. Take a minute and relook over this portion of the video if you have any questions. Okay, I want to take a minute to recap what we did on example question 2. So we were given the molar concentration of the weak acid. We were also given the Ka for the weak acid, and we wanted to find hydronium concentration and pH. So we set up our ice table. We included the initial molar concentration for the weak acid. Both the products are 0. We plugged in what we have for the change, and that is minus x and plus x, and then the equilibrium is going to be the initial and change together. Okay, so what's highlighted is what we're going to need to plug into Ka. We then set up Ka by plugging in all of these values. Okay, our 2x values for the products are at the top, x squared over our reactant, 0.10 minus x, and we set that equal to the Ka, which is 1.3 times 10 to the negative 5, and then we solved for x, which was equal to hydronium concentration, and we know that pH is equal to negative log of hydronium concentration, So we took our x and plugged it in here. All right, the longest part was the quadratic, or if you did graphing, and that probably took the longest as well. So what's easy in these problems is just to get lost in what the objective is. So always go back to your ICE table and ask yourself, okay, what is x equal to? What am I solving for? Why am I solving for x? And you'll notice that x corresponds with hydronium, and that was the point of the problem. All right, let's move on to our next section. Okay, so how does concentration affect acid dissociation? Concentration does affect how much an acid dissociates, the percentage of how much dissociates. The Ka is always going to be the same, or Kb if you're looking at a base. But acid dissociation, it can be defined by the following equation. Percent dissociation is defined by the concentration of HA that's dissociated over the initial concentration of the acid times 100. And to be specific about what I mean by that, HA dissociated means that it did this, okay? It just ionized. Another way to put that is HA reacting with water makes hydronium and A minus. Okay, these two equations right here are synonymous. This doesn't show the water, but it is implied that HA is being dissolved in water. So when we're talking about the amount or the concentration that's dissociated, we're really asking how much of the acid is in this form, is in the A minus form. So how much actually ionized into A minus. The basic principle is as concentration decreases, so as the initial concentration of HA, as it goes down, the percent dissociation actually goes up. There's an inverse relationship to that. The reason for that is as you have fewer HA molecules around in water, there's more water available to each HA, and water is really what's doing the dissolving of the HA, of the weak acid. So as you have more water around, it's able to allow for HA to dissociate into H plus and A minus. So the reason then is because there's more water available at lower concentrations. So let's look at how we can calculate this ourselves, can calculate percent dissociation ourselves. All right, example question 3 asks us to calculate the percent dissociation of 0.40 molar, oh gosh, what is this? Hypochlorous acid. It's early in the morning and sometimes chemical formulas can throw me off, and I'm sure the rest of us as well. And we're given the Ka. The Ka is equal to 2.9 times 10 to the negative 8. All right, so from this, when we're talking about dissociation, remember, we're really just talking about the acid dissolving in water. So that means I have hypochlorous acid plus water, and it's creating hydronium and hypochlorite. Okay, from this we can set up an ICE table like we'd normally do. Let's plug in the values that are given to us. 0.40. We don't care about water. It's not involved in the ICE table. And for both products, it's 0 before the dissociation occurs. The change is going to be minus x, and plus x. And then at equilibrium, we have 0.40 minus x, and x. And the reason we're setting up an ICE table is because to determine percent dissociation, we have to know the amount of HA that dissociated over the initial HA concentration times 100. We know this. We know initial. That's right there. We also obviously know that I have to multiply it by 100. That's given. So what I'm looking for is this number. That is going to be equal to my x, because remember, this is the dissociated form of the acid. Okay, so let's take this information that's found in row E, that's highlighted, and plug it in for Ka. Remember, Ka is equal to products over reactants. So that means it's equal to x squared over 0.40 minus x. And that's equal to 2.9 times 10 to the negative 8. All right, so we're basically stuck at this point to solve for x. We need to know what x is equal to. X is equal to what? Because we know that's going to give us the concentration of hypochlorite, which is equal to HA dissociated. Okay, these are all equal to each other. X, hypochlorite, and HA dissociated. And remember, what I'm looking for is HA dissociated to solve for percent dissociation. Okay, here I'm going to teach you how to use the assumption in these problems. The assumption that we're using is that this minus x is so small. So x is so much smaller than 0.40 that it is considered negligible. All right, so that means we're basically going to cross it off here, okay, in my Ka expression. So notice it's going to simplify this problem a lot so that you won't actually have to do the quadratic. So that means x squared over 0.40 is equal to 2.9 times 10 to the negative 8, which if we cross multiply this over, that means 0.40 times 2.9 times 10 to the negative 8 is equal to x squared. And if I square root on both sides, that tells me that the square root of 0.40 times 2.9 times 10 to the negative 8 is equal to x, plus or minus x. Obviously, we're going to take the positive value of that. So go ahead and plug that in your calculator, and let's see what we get for x. Okay, for x, I get 1.077 times 10 to the negative 4, which again is equal to hypochlorite, which is equal to HA dissociated. Okay, so I just solved for what I needed. I solved for HA dissociated. So let's go ahead and take that and plug it into our percent dissociation equation. So I'm going to erase everything else so we have a little bit more room. So we have percent dissociation is equal to the number we just solved for, 1.077 times 10 to the negative 4 over our original concentration, which is 0.40, times 100. See what we get. .7% dissociated times 10 to the negative 2. There's still a couple things we have to do. We have to verify that our assumption was acceptable. And I also want to talk about this 2.7%. So this 2.7% is a low number. So it tells you that it's a pretty weak acid, because strong acids, remember, ionize 100%. They completely ionize. So this tells you this is a pretty weak acid. Okay, let's go ahead and check our assumption. I'm going to erase this down here. Okay, the assumption is only valid if, write this in this column, assumption that my x is so much smaller than this 0.4 that I can basically eliminate it. Assumption is valid if x over my initial concentration times 100 is less than 5%. Well, I can already tell you it is based on this equation right here. This equation is essentially x over my initial concentration. But this is the formula that you're going to be using in general in class. It's going to be your x, or your change, is going to be less than 5% of the initial. So let's plug it in again. 1.077 times 10 to the negative 4 over that 0.40 times 100 is equal to 2.7%, which is indeed less than 5%. So I put a big check mark. The assumption is valid. That means it stands. Okay, that means I don't have to go back and correct it. If assumption, or I'll make it even simpler terms, if it is greater than 5%, must go back and use quadratic. The reason the assumption is so nice for us is because it bypasses the quadratic. We don't actually have to use it. But if the assumption is not valid, you cannot cross this x off. It has to stand, it has to stay. And then when you're solving for x, that means that you end up with a polynomial. And you have to solve for x using the quadratic formula. So this, again, is only valid if the change is less than 5%. Okay, so in B is the same exact question, except notice it's a lower molarity. Now, if you go back to the previous page, you'll see that we talked about how as concentration of a weak acid goes down, the percent dissociation goes up. So what I want you to check in this problem is solve for it and ask, does percent dissociation increase? Okay, it should increase. That means your answer should be greater than 2.7%. So I'll let you do this on your own, and you can check with me after to see if you do in fact get a higher percent dissociation. All right, let's move on to polyprotic acids. Polyprotic acids have more than one acidic proton. So as an example of a polyprotic acid, be something like H2SO4. This is sulfuric acid. There are two acidic protons here. There's also H3PO4. That's phosphoric acid. This has 3 acidic protons. This right here, this first one is called a diprotic acid, diprotic. And the next one is called a triprotic. All right, so we have more than one acidic proton. Part B, the first acidic hydrogen has the highest Ka value. Each subsequent Ka decreases. Okay, why do Kas decrease? So let's just look at what this means. So when I put H2SO4 into water, there are 2 dissociations that happen. The first dissociation is when the first proton is given to water, and I end up with hydrogen sulfate and hydronium. This is referred to as Ka1, acid dissociation for the first hydrogen. Then a second dissociation will happen. Hydrogen sulfate will react with water to form sulfate and hydronium. This is referred to as Ka2. All right, why do the Ka's decrease in value? So a very condensed answer to that is, as this first hydrogen leaves, I end up with a negative charge, right? Now, in order for the second hydrogen to leave, which is positively charged, it has to be given away to water, and now I have a resulting charge of 2 minus. That means it is more difficult to give away a hydrogen which is positively charged from a negative species. And each time a hydrogen is given away, the resulting conjugate base, this is the conjugate base of sulfuric acid, the resulting conjugate base is more negative, right? So in this scenario, sulfuric acid had a 0 charge. It was neutral. When it gave a hydrogen away, it became HSO4 minus, so it has a 1 minus charge. Then when HSO4 minus had to give away a hydrogen, it became SO4 2 minus. So each time a hydrogen is given away, there's an additional negative charge, and that is an unfavorable process. Compounds desire most to be at a neutral charge, as neutral as they can. They're most stable at their neutral charge. So for every hydrogen given away, the negative charge increases, which is unfavorable. All right, that's it for this lecture. Our next lecture will finish the last 5 pages for these notes, chapter 18 notes. Again, work on these problems with each other, check with me, and I will see you guys next time.